think we are ready to start. So good. We are happy to have Leo Coregliano, I think is hopefully the right pronunciation, from Chicago, and he'll tell us about the abstract chromatic number.
Okay. Thank you everyone for coming. So as Avi said, I'm going to talk about the abstract chromatic number. So if you ever taken a class in a basic class in extremograph theory, you are bound to have seen one of the classic theorems, which is Turans' theorem, right? And Turans' theorem, what it says is that, well, say that you wanted to maximize the number of edges, and in a graph that doesn't have any L cliques, that is, there's no L points that are all connected to each other. Well, then Turan found out that the best thing you can possibly do is to take L-1 parts, approximately of the same size, and put a complete partite graph. That is, you have edges between the parts, but not any edge inside the parts. And that's what later we call the Turan graph. And this is the best possible thing you can do in this theory. Now, what is surprising is that later on, Erdos, and Simonovitz generalized this theorem, and they noticed that, well, if instead you forbid some family of graphs, non-induced graphs, then if you try to maximize edges in this F-free graph, then the best thing you can do is still the Turan graph, except that the number of parts that you're going to use is based off of the chromatic number. So you look at all your family, you compute the chromatic number of all the graphs, take the minimum of those, subtract one, take those many parts, and take the Turan graph there. Now, there's a small difference between this theorem and Turan's theorem. Turan's theorem is really optimal. Here, it's optimal except for a small error, which another way of seeing this is that if you normalize by, say, n choose 2, which is the usual normalization for edges, then the best density you can get looks something like this. So it's 1 minus 1 over chromatic number minus 1, plus something that goes to 0 as the size goes to infinity. Now,
let me just stop to make sure that everybody is happy with this, because I think things later will depend on understanding this theorem. So
yes, and let me also say, if you have any questions or you think I'm going too fast, feel free to interrupt me. It's not a problem. I can clarify questions on the fly. Okay, so
can you? It was a bit too fast for me. Can you go back from it? So why is it O(n) squared, and when you write Tn subscript this number, it means it means that you have bunches of this chi f-1 vertices.
Yes, you take your set, you partition it into chi f-1 parts, approximately of the same size, and you put edges between the parts, but never inside the parts, right? So it's a complete partite graph, and the number of parts that you put is chi f-1.
So in particular, this graph can be colored by chi of f-1 colors, obviously, by construction.
Yes.
And it's exactly a maximal one with this chromatic number in terms of the number of edges.
In terms of the number of edges. And that is kind of the intuition of why this theorem holds. This is the, in a certain sense, this is the worst case scenario that your graphs could look like if they can still be colored in chi f-1.
So essentially it means that to prevent the graph to have a bad subgraph, it's enough to do it by coloring. So the coloring is what prevents.
Yes,
the coloring
exactly,
is my tool to prevent to have this bad graph.
Exactly, because what happens is that if your graph is colorable with, say, C colors, then you certainly cannot find it in a complete part with C-1, a complete partite graph with C-1 parts, because if you could, that would show that your graph is actually C-1 colorable. Because somehow you look at the way that it's inserted in this complete partite graph, and edges can only be between parts, so that gives you a coloring of your original graph. So that is kind of the intuition of why this term is true.
Yeah, but I think that Lior was sort of asking about the other direction. It doesn't matter what the graphs you want to forbid are, except for one parameter. What is their chromatic number? Anything else about them you can forget. As long as you forbid this coloring, then you are fine.
Exactly.
Wow, that's really strong. And
yes,
what's edge density in this case?
You can calculate it. I mean, it's not
edge density is just to take the number of edges.
The number of edges out of the n choose 2.
Yes, exactly, out of n choose 2. So it's a number.
The number of non-zero entries in the matrix. Okay.
Yeah.
Yeah, but normalized by n choose 2. So yeah, but you're right. This theorem is quite impressive. At some point, it was called the fundamental theorem of extremal graph theory. That's how important this theorem actually is. Now, let me talk also about a different theorem, a different direction where you can generalize this Turans theorem. This was a theorem by Erdos, and what he studied was, well, let's do the same thing as we did for the Turan theorem. So we look at KL-free graphs, but instead of trying to maximize edges, let's try to maximize small cliques. Of course, cliques here need to be T less than L. So I'm going to look at maximum density of KT. And Erdos said, well, actually, the best thing you can do is still the Turan graph. So it's kind of like what matters is that you're taking KL-free graphs. If you're trying to maximize whatever cliques are there, so if T was 2, it was just an edge. If T is larger than 2, say maybe you're trying to maximize triangles, the best thing you can do is still the Turan graph, so L-1 complete part-type graph with size parts almost of the same size. And this is the density that you see. This is just a computation. It's not very important exactly what this is.
But then density out of what? So now you take the number of KT out of the number of KT that you have in a complete graph?
Exactly, which is n choose T. So density will always be normalized by the maximum possible that you would expect. So here is normalized by n choose T. Now, more recently, Allen and Schickerman noticed that in the same way that Erdos Simonovic's theorem generalizes Turans theorem, you can also generalize this Erdos theorem to use the chromatic number as well. So if you have a family F and you're looking at F3 graphs, and again, you're trying to maximize the density of KT, then the best thing you can do is, again, the Turan graph with chi F minus 1 parts. And this is the density that you see, which you can see it's essentially this expression, but you substitute the L here by the chromatic number because it's the same graph. You're using chi F minus 1 parts. Okay, now in a different direction, people more recently have been looking at some sort of different types of generalizations of these theorems. So for instance, here's Erdos-Simonovic's theorem again, so that we have it in mind. So for example, Pack and Erdos have observed that this theorem still holds if you consider ordered graphs. So for ordered graphs, you think that you have a graph and you have ordered the vertices in some way, right? And then you take some family of ordered graphs and you forbid that family non-induced. So you cannot see a copy of a certain ordered graph. And then you ask yourself, well, let's try to maximize the edge density of this guy. And what they say is actually the same sort of result holds. The best density you can see is still this formula, except that you're going to use a different type of chromatic number, which is called the interval chromatic number. Now, this has the same definition as the usual chromatic number, but each of the color classes is required to be an interval of your order. So you're trying to color the vertices of your graph, but remember the vertices are ordered somehow. So you require, say, if you look at all the vertices that receive red color, that needs to be an interval. So you cannot see, if you look at the order, you cannot see something like red, 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 blue, red again, because that violates an interval. It needs to be an interval that gets a color, then another interval gets another color, and so on. And you still have the restriction that no edge is monochromatic. And so that's the definition of the chromatic. And it completely characterizes the maximum edge density that you can have on F3 graphs, where F is any family of ordered graphs.
So again, what can you repeat again what's the interval? By interval, you mean that
interval means an interval of the order, right? So you think of an order, an interval in the order is any set such that if I give you 2 points in the set, if a point is in the middle of them in the order, then it must also be in the set.
Leo, the vertices, you can think of them as one through n. They are lying on the real line.
Yes.
Okay, so an interval is an interval.
No,
Yes.
no, an interval I see. I didn't understand what the coloring is.
Oh, yes.
You
So
got
now
the
the coloring, the coloring, a proper coloring of an interval graph, of an ordered graph, is a coloring that, as usual, you cannot assign the same color to endpoints of the same edge, but each color class, so if you look at all the vertices that receive, say, color red, needs to be an interval of the order, right? Remember, the vertices are ordered somehow. Right? So each color class needs to be an interval. That's what's called interval chromatic. Okay?
You have a color that.
Sorry.
The color referred to two things: the graph structure by this not being there, and the order structure, which is just project all the colors to the real line.
And they need to
not the colors. The vertices are on the real line, and the red guys will be numbers 1 through 11, and then the green ones will be 12 to 72. That's all. But it should be a legal coloring.
Yes, exactly. So it needs to be the colors need to be an interval, but it also should be a proper coloring of the graph.
So if you had edges between every I and I plus 1, then you'd have to use n colors.
Exactly. So you can see that the interval chromatic number can be way higher than the usual chromatic number. Some things are interesting, and I'll go into more details. These other types of chromatic numbers have some interesting properties as well. Now, let me proceed, and then now, if everyone is reasonably happy with the interval chromatic number, let me give you a slightly different result that was discovered independently from this, is this one. So if instead of giving an order of the vertices, I give a cyclic order of the vertices, so in the same way that you could think that the vertices are placed in the real line, you could think that they're placed on S1, right, on a circle. So now you don't have exactly an order, but you have a cyclic order. And they observed that the same result still holds, except that now you need to use something called the cyclic interval chromatic number, which again has exactly the same definition, but now the intervals here are cyclic intervals, right? It's some part of the circle, right? So they discovered this. There is this other chromatic number that holds in this case.
What exactly does it mean? The same holds? Like what is the?
Oh, the same holds means if you have a family of these cyclically ordered graphs, a family F, and you consider the F-free cyclically ordered graphs, and you try to maximize the number of edges, the best possible thing you can get is this value, but you replace this guy.
So what exactly does it mean to be F-free when you are cyclically ordered?
Oh, F-free means, I give you a very big cyclic ordered graph, say, and I have said that they're F-free, and F is a family of cyclic ordered graphs, right? So you look at it and you see whether you can find a copy of this small cyclic ordered graphs there. And I'm saying that you never can find it, right? And a copy means the relative cyclic order is the same as you see in the graph, and it's a super graph, right? So you can add edges, but you cannot remove.
Okay, so you just need them to be ordered, like
in the same way
of the subgraph as to be ordered the same.
Yes, but what's important here is the relative ordering, right?
Yes.
Okay. So everyone happy so far? Okay, good. So the next theorem that I want to talk about that appeared in the literature is that the same holds for edge order graphs. So if instead you had an ordering of the edges of the graph, then again the same result holds, and it holds using what is called the edge order chromatic number, which I'm not going to get into details here because it has a complicated formula, and at the end of the day I'm going to talk about something that's going to cover this, so there's no point in me explaining this particular formula that's very complicated here. But in any case, if you look at this pattern, right, you might ask yourself, is it possible to prove like some sort of meta theorem, an abstract theorem that looks like this? The same holds for graphs with extra structure, whatever extra structure means, as long as I replace the chromatic number by an appropriate chromatic number, which I'm going to call abstract chromatic number. Right? It's a very natural question to ask. Now, before we proceed to talk more about this question, let me talk about a little bit of properties of these chromatic numbers, which are quite surprising. So these concern computability of these chromatic numbers. So as we know, the usual chromatic number is NP hard to compute. But if you think about it for some time, you're going to see that the interval chromatic number actually can be computed very fast. It can be computed in linear time, because all you have to do is do a greedy algorithm. You start on your interval, look at the first point, and you keep coloring the same color as long as you're not violating the coloring. And once you cannot color with the same color, you change the color, and you know that this is the best you could have done so far. So a greedy algorithm works in this case. So you can actually compute this in linear time. By the same token, the cyclic chromatic number, cyclic interval chromatic number, can also be computed fast. You have to do a small trick, but it's still essentially polynomial. But if you look at the edge chromatic number, things actually look pretty bad, because I didn't tell you what's the formula, but even if you look at the formula, you're going to see it's not really clear how you would even give an algorithm to produce that. It's not even about giving an efficient algorithm. You don't know how to give an algorithm to compute this thing. So the question that we might ask ourselves is, well, if that conjecture of the previous slide holds and I can actually construct such an abstract chromatic number, should I even expect this thing to be computable with an algorithm? Okay. So in this talk, I'm going to talk exactly about these two things. So the first part, I'm going to talk about this abstract chromatic number, and the second part, I'm going to talk about the computability of this. Okay. So abstract chromatic number. So we want to talk about graphs with extra structure. So if I'm going to talk about this, I might as well talk about a slightly more general setting, which is that of general combinatorial objects. And if we think about the problem that we have in our hands, we need to understand what concepts need to make sense for us to produce an abstraction of all of this, right? And we see that we talked about the notion of F-free graphs and the notion of density. Both of these notions rely on the concept of sub-object, right? It needs to make sense that I have a combinatorial object, and the notion of sub-object in this combinatorial object needs to make sense. To do that, we're going to need a setting borrowed from model theory. So here are the basic concepts of model theory that we're going to need. So we start by fixing a finite language of predicate symbols. So this means that this is just a finite set, and each element of the set is a predicate symbol, and it has an associated arity, which is just a positive integer. Now, if I'm given such a language,
some people probably have never seen it, so maybe give an example.
I'm going to give an example at the end of this the end of this slide.
Okay,
a very useful example, but let me give all the definitions, and they will stay on the slide, so don't worry, they will not go away once I get to the example. Okay. So if I'm given such a language, an L structure is just going to have a vertex set, and for each predicate symbol that I have on my language, remember it has an arity, right? So I'm going to associate a k-p-array relation. That is just a set of k tuples where k is this arity of this predicate. And that's an L structure. Now, a first order theory is going to be a set of axioms over this language L. So this language L has predicate symbols, and I'm just going to put some axioms on top of that. And I'm going to say that a model of my theory is going to be an L structure that satisfies all of these axioms. And the idea of these definitions is that a general combinatorial object for us is going to be a model of some fixed theory P. Okay, so let's give an example, right? So here's the classic example, is going to be the most useful example for us: the theory of graphs. The theory of graphs, the language has only one predicate symbol, E. This predicate symbol is binary, and it's trying to encode adjacency, the adjacency relation. Now, if the predicate symbol is going to encode adjacency relation, these are the axioms that we want our theory to satisfy. If I give you a vertex, it's not adjacent to itself. So I'm going to assume simple graphs, no loops. And if I give you two vertices, if x is adjacent to y, then y is adjacent to x. Okay. Now you can see that with these definitions, graphs corresponds to models of this theory, right? Because a graph is nothing more than a sum vertex set, and then a set of pairs.
Is KE?
What?
KE in this number, in this KE is equal to 2.
Predicate. Is a predicate, is the relation.
Yes.
And
Yeah, E is a predicate symbol, and the arity of this predicate symbol is 2, so it's a binary relation. Yes.
Sorry, I'm not sure what's a predicate and what's
so a predicate is just going to be an element of this language, right? So this language has a single predicate, an element, E, called E, right? And it's going to be a binary predicate, right? So when you're talking about E is encoding adjacency, right? So you're going to say how many vertices are adjacent, and it's 2, right? So it's a binary relation, right? So K of E is 2, right? And then you have to say, what are the axioms that this thing is satisfies? The first axiom says no loops, right? So no vertex is adjacent to itself. And the second one says adjacency is actually symmetric. So if x is adjacent to y, then y is adjacent to x. That okay? And with this thing...
One more question. Is there a difference between having a set of predicates and a language of predicates? As in, is the word language imposing any additional structure on the list of predicates?
Yeah, so the only additional structure is that each element of the set has an arity, has this associated KP that is saying, oh, this guy is binary, this guy is ternary, this guy has arity 5. That's the only extra structure. That's what changes a set from being a set to a language. You have this extra arity. In our case, I should say, yeah, I should say that I'm working a restricted setting of model theory. A language in more general model theory can have more things, but for us, it's just going to be this.
So I'll just verify that, first of all, that Lior is satisfied, and that you can see, for example, that he could have he could have removed the second axiom, and then it would allow directed graphs, or he could have made another set E of RET3 and then describing 3 uniform hypergraphs and so on.
Exactly. Yeah, in fact, so you're anticipating my next slide, in which I think it's 2 slides from now that I'm going to give some more examples of this. But okay, so is everyone clear with the notion of these models and first order theories for now?
So just to make sure, an L structure in this example is a graph.
Well, an L structure doesn't require you to satisfy the axioms, but the model
for this L.
Yes, an L structure is just going to be a set with binary relations, right? But it could be a directed graph at that point. But the model of this theory is required to satisfy these axioms. So a model of the theory T graph is a graph. It's an L structure that satisfies these axioms, therefore it's a graph, right? Does it make sense? Okay. So I have one more requirement of our theories, which is we're going to assume that they are what are called universal theories. So our axioms are not going to be anything. They're going to be of a certain specific form. They're going to look like this. So it's a bunch of universal quantifiers and then an open form. So an open form is just, there's no quantifiers hidden in this form, right? Now, the reason why we need the axioms to be of this form is exactly because we want the notion of subobjects to be well defined. Because think about it for a second. If I give you a model, right? So remember, this has a vertex set, has a bunch of relations, and it satisfies the axioms of my theory. Now I give some subset of vertices, right? So take these vertices, take a subset. I can restrict my attention on my model to the subset of vertices, right? So this is what's called the submodel. I define a new structure, which is I take the vertex sets to be this smaller set, and I take all my relations and I restrict to this set. So I only look at tuples that are completely contained in that. Now, because I just restricted my space and all of my axioms are of this form for every x something holds, of course, this thing also satisfies my axioms because, well, it's a for-all quantifier, right? So this means that every time I have this big object and I restrict my attention to a smaller place, it still satisfies the axioms. It's still a model. And so this is why we want them to be universal. It allows the definition of submodel. And another concept that I need to review, or if you have never seen, is that of isomorphism. It's the natural definition. If I give you two models, let's say that they're isomorphic, if there is a bijection between the vertex sets, that preserves the relations, right? So if you take some tuple and it satisfies the predicate P in the structure M, then when you compose with the function, it's going to satisfy the predicate P in the other structure, if and only if. So this is the analog of saying two graphs are isomorphic if there is a bijection between the two vertex sets that preserves adjacency and preserves non-adjacency, right? So it's if and only if. So preserves when the predicate is true and preserves when the predicate is false. So this is the notion of isomorphism. And with these two, yeah, go ahead.
So where do you see here the preservance of adjacency?
Oh yeah, so in the case of graphs, we have a single predicate symbol. So say P here was our E, that was the adjacency, right? And this is saying, well, a certain tuple, in our case is going to be a pair, is adjacent in the first graph, if and only if, when you compose with the function f, they are adjacent in the graph n. And so this is, but it's if and only if, so it's preserving
okay.
both adjacency and non-adjacency.
RP is the set of functions in my language, and
RP is the set of tuples that satisfy the predicate, right? Okay. RP is the set of tuples that satisfy the predicate P. And in the case of graphs, P is E, right? So essentially, you're asking what pairs are adjacent.
Thank you.
Okay. Now, with these two notions, this allows us to define densities. And here's the definition of density. It's going to be essentially the same that we get in the graph case. So if I give you two models M and N, the density of M in N is computed as the normalized number of unlabeled copies of M in N. What you do is you look at all possible sets of vertices in the larger model, and you count how many of these induce a model that is isomorphic to M. And then you normalize by the maximum possible number that you could see, which is just a binomial number of vertices of N choose number of vertices of M. So this is the analog of saying, oh, what is the triangle density in a certain graph? Well, you look at all possible sets of size 3, and you count how many of them give triangle, and you normalize by N choose 3, right?
A question.
Mm-hmm.
Yeah, what about, I mean, you are looking at forbidden graphs, not as induced subgraphs, but as... Yeah,
yes, so in here, when I'm talking copies here, it's, if you apply this for graphs, is induced. At this point, it's induced. Now, of course, if you're talking about F-free graphs and you want non-induced, you can also always say, okay, I want to forbid this family non-induced. Well, it's the same as take this family, close it under supergraphs, and forbid that induced, right? So induced is the more general setting than the non-induced, right? Okay, so let's give some more examples of universal theory. So we saw the theory of graphs, and if you recall the axioms, we only use universal quantifiers. So that theory was universal. Let me give you another example that actually is not symmetric. So for instance, the theory of strict linear orders. This is also a universal theory. You have, again, a single predicate symbol. It's a binary predicate symbol. And here are the axioms, right? So every x is not less than itself. If I give you 2 points and they're different, then one of them needs to be less than the other. So x less than y or y less than x. And if I give you 3 points, you should have transitivity, right? So if x is less than y and y is less than z, then x is less than z, right? So this is the theory of strict linear orders. And it's universal, right? Because the quantifiers that I'm using here, they're only universal quantifiers. Now, another theory that we kind of already bumped into is the theory of cyclic orders. The theory of cyclic orders, again, it only has one predicate symbol, but now it's a ternary predicate symbol. And this is the axiomatization of the theory. There's an axiom saying, oh, it's cyclic, so if you swap the arguments around in a cyclic fashion, then the predicate still holds. If you swap them in a non-cyclic fashion, then it doesn't hold. You have this is the transitivity version of the cyclic order, and then you have the totality version of the cyclic order. But again, what's important here is not the axiomatization itself, but look at this, you only use a universal quantifier, so this is also a universal theory. Now, I should say that a lot of other objects that we have seen are also universal theories. So for instance, edge-ordered graphs, there is a theory of edge-ordered graphs, it's also universal, but the axiomatization is way more complicated than this. It would probably take the whole slide, so I didn't bother putting it here. Okay, is everyone reasonably clear on these definitions of basic model theory so far? Okay, so now let's spice things a little bit more. If I give you two theories, I can actually do some neat constructions on top of them. I could, for instance, take the disjoint union of these two theories. So by disjoint union of two theories, what I mean is each theory has a language. I take the disjoint union of the languages and I put both of the axioms of T1 about the part of T1 and the axioms of T2 about the part of T2. Now, this operation is neat because it allows you to do operations like this. If I give you a theory T and I take, say, the disjoint union with the theory of orders, then the theory that I'm producing here is the theory of linearly ordered models of T. So the models of this disjoint union are just going to be usual models of T, except that I somehow ordered their vertices. Now, you can see why that's going to be useful for us, because if T in particular is the theory of graphs, what I'm talking about here is the theory of ordered graphs. And if the theory of graphs, instead of take a union with, say, the cyclic order, that's the theory of cyclically ordered graphs. So you can see why this sort of operation is going to be useful for us. Now, the other operation you can do on a theory, which is kind of silly, but is also going to be important, is that of adding axioms, right? You can always start with some theory and you can add extra axioms. Now, this is important because this is exactly what allows us to talk about F-free models of T. You take a family and you say, well, I want to consider only models of the theory that do not have copies of these particular guys, right? So this is what's called this fork T of F. So let me give you an example. Say that I wanted to talk about triangle-free graphs. So all that you have to do is you take the usual theory of graphs and you add this axiom here, right? That says every triple is not a triangle, right? And this can be done in general. In the general case, if I give you some family F, all that you have to do is for each graph on your family, you construct a formula which is called the open diagram of F, which completely describes that guy that you want forbid. And then you put an axiom that says, well, for every tuple X, I do not satisfy this formula. I do not see a copy of F. Right? So this is how you take induced F-free graphs. And as I said before, if you wanted instead to talk about non-induced, there are very simple tricks that you can do. You can take the family F, close it upwards, and now this is a new family F prime, and now if you forbid F prime induced, is the same as forbidding F non-induced. So this also captures forbidding non-induced. Now, one last thing I want to talk about this forbidden.
Sorry, a question. So when you do such a rule like the open F, you immediately cover all of its isomorphisms, right?
Yes.
It seems like a rule like this cannot distinguish between two isomorphic graphs.
Yes, exactly. But again, when you're saying F-free graphs, you also cannot distinguish isomorphic copies, right? A copy of a triangle is a copy of a triangle. It doesn't matter where you found it, right? Does it make sense?
Yeah. Although what happens in the ordered graph, in the ordered sense?
Well, in
So
the
you
ordered
have-
graph, yeah, in the ordered graph, the order itself is part of the model, right? So when you look at isomorphic copies, the order will be there to be telling you, is this isomorphic or not? So for instance, let me give you an example, right? Take a path of length 2, right? But let's order it in 2 non-isomorphic ways. One way that you can order the path of length 2 is say 1, 2, 3 in the usual order. Right? But you could also order it in 2, 1, 3, right? That's a non-isomorphic order, right? Because it looks different, right? And copies of the first are completely different than copies of the second in the theory of ordered graphs, right? Because the theory of ordered graphs, the notion of isomorphism says the order must also match.
Okay, thank you.
Sense?
Yeah. Totally.
The notion of isomorphism takes into account all the predicates in your language. All of them.
Exactly. It needs to preserve the whole structure.
Yeah, no, it was more a question about the resolution of this open machine. It's like it cannot, you cannot exclude something in a resolution finer than isomorphisms.
Yes, you will only see something isomorphic, but isomorphism, it depends on what your language is. The language can be rich enough to detect other things, right?
Yeah.
Okay. So one last thing I want to talk about this form construction is that you can see theories always as form F for some F, right? So say if I give you a theory T, you can think of it backwards, right? You can think that you start with an empty theory that doesn't have any axioms, right? It's over some language. But then if the theory doesn't have any axioms, you have all possible structures. But then you say, well, I actually wanted my theory P. So you look at all the structures that are not models of your theory, and you say, well, my theory is nothing more than take the empty theory and forbid all these guys that I want to say they're not models. Right? So every theory can be written as form F for some F. Right? Now, of course, if you do it naively, this family is going to be infinite. Right? You're going to forbid. So, for instance, triangle-free graphs, if you just do this naively, you're going to forbid any graph that has a triangle in it, instead of just saying, well, I'm just going to forbid the triangle itself, right? So some theories, you can produce simpler families F that maybe are finite, but some theories you cannot. And if you do it naively, in general, you get an infinite family. Okay, now, before I proceed, I need to give you one last definition of model theory, and that is of open interpretation. So an open interpretation is going to give you a way of transporting information between different types of objects. So here's the definition. An open interpretation from a theory T1 to a theory T2 is a function that maps each predicate of T1 to a formula in T2. And this formula is required to not have any quantifier. And also this map needs to satisfy the following property. Every axiom of T1, once I apply the map to that, it becomes a theorem of T2. That is, T2 can prove that that thing is true. Now, this is kind of encoding a local combinatorial construction. But the local combinatorial construction goes in the other direction. So here's what this is encoding. If I give you a model of T2, and I give you such an open interpretation, there's a way of constructing a model of T1 as follows. The vertex set is going to be the same. And for each predicate symbol of T1, what I'm going to do is, I look at the predicate symbol, and my open interpretation gives me a formula, right? And then I ask, what are all the tuples that satisfy this formula? And if it satisfies the formula, I'm going to declare that the predicate of T1 is true here. And if it doesn't satisfy the formula, I'm going to declare it to be false. So it gives you a combinatorial construction from T2 to T1. Now, let me give you some examples because this can look quite abstract. And let me start with very trivial and simple examples. So for example, if I have a theory T1, we saw that we can add axioms and form a new theory T2, right? Every time I do that, there is a very simple open interpretation from T1 to T2 because I can just act identically And then, of course, because I only added axioms, T2 can prove all the axioms of T1, because in particular, they are axioms of T2, right? So, for example, there is an open interpretation that goes from the theory of graphs to the theory of triangle-free graphs. And the construction that goes in the other direction corresponds to the trivial construction, which means if I give you a triangle-free graph, in particular, it is a graph, right? So you can just forget that it doesn't have any triangles. It's perfectly fine. Or more generally, if I give you an F-free graph, in particular, it is a graph, right? So this is what is called the axiomatic interpretation. It's one of the trivial ones. Now, let me give you another trivial example. We saw that we can also form disjoint union of theories, right? And if you can form disjoint union of theories, you can always inject theory T1 inside the disjoint union of T1 union T2. And you act identically on all the predicates. So for example, you can put the theory of graphs inside the theory of ordered graphs. And the construction that is going in the other direction is corresponding to erasing the order. That is, every order graphs, if you forget about the order, it is in particular a graph, right? So this is what is called structure erasing interpretations. So far, so good. Now, let me give you a non-trivial example here. So for example, say that I gave you two linear orders, right? So there's a vertex set and somehow I gave you two linear orders. Now, one combinatorial construction you could do is you could say, let's form a graph in which I put an edge every time these two linear orders agree, right? If they agree, I put an edge. If they disagree, I don't put an edge. Well, what you're actually doing there is you're considering this particular open interpretation. You're declaring the edge relation to be exactly the formula that says these two guys agree, right? So this formula is taken there. Right? And that the construction is exactly what I said. That this construction is taking these two orders and constructing a graph, putting an edge exactly when they agree. Okay? Right, okay, so what does this have? So far we talked about these general combinatorial objects, we talked about this open interpretation. What does this have to do with our original Erdos-Simonovitz theorem? Well, it's based off of this definition. So here's how you reason about this. So say you start with some open interpretation that is from the theory of graphs to some theory P. And then I give you some T, some number P. I'm going to say that the Turan density is going to be this formula here. So what you do is you look at all models of size n. So this is the set of models of size n. You apply your construction. So this IN is applying this local combinatorial construction. Now you have a graph on your hands, right? So you can compute the density of T cliques in this graph. You compute the density of T cliques in this graph. You maximize over your choice of this model, and you take the limit as n goes to infinity. Okay. Is everyone clear with what this formula means so far?
It's not obvious what you are not telling us what this interpretation is.
Yes, I'm going to tell you in a second.
Yeah.
So let me just say a couple of technical details about this. If you don't understand, you can ignore the next two topics. The first topic is that the soup here, you might as well think of it as a max because the set is finite. The only reason I write soup is because it could be empty. This is what's called the theory be degenerate. And the other is that you might complain that this is a limit and maybe you might want to take lim soup or lim inf. In fact, the sequence is actually not increasing. There's an argument that says the sequence is not increasing. But that's not that important. Let me tell you why is this actually capturing the Erdos-Simonovitz theorem. So for example, suppose that your open interpretation was that usual axiomatic interpretation, right? So remember, you have this open interpretation that says you can interpret the theory of graphs in the theory of F-free graphs, non-induced F-free graphs now, right? What was the combinatorial construction over there? It was just ignoring the fact that you are F-free. Every F-free graph in particular is a graph, right? So when you're doing this computation here, what you're doing is you consider all possible F-free graphs of size n. You apply your construction. Well, your construction doesn't do anything. So take an F-free graph of size n and maximize the density of T cliques. and then let the size of the graph go to infinity, right? So this is how it was capturing the Erdos-Simonovitz theorem, right? You're just looking at the set of F3 graphs and trying to maximize p cliques in them. Is that clear? Can everyone see that this is actually capturing the Erdos-Simonovitz theorem?
You don't see here who's the maximizer, right?
Well, no, it's not really capturing the theorem, but it's capturing the problem, right? You're asking, let's maximize, say, the edge density, right? So this value is going to give you the value of the maximum edge density as employed. It's not really capturing the theorem. I'm not saying, oh, from this you can deduce it's the Turing graphs. No, it's just capturing the problem, right? This is the problem of the Erdos-Simonovitz, right? They're essentially asking, what is this value, right? Does it make sense? Okay, but notice that it was also capturing the problem for the other generalizations of the Erdos-Simonovitz theorem that we were seeing. Because, for example, if instead I take my open interpretation to be a certain composition of two open interpretations, and the composition looks like this. S here is going to be the structure raising interpretations from graphs to order graphs, right? And A is going to be an axiomatic interpretation that maps order graphs to F-free order graphs for some family of order graphs F. Then, when I take this guy here, what this number is computing is you take an F-free order graph, you forget its order, compute the density of T cliques, maximize over your choice of F-free order graphs, and take the limit as n goes to infinity. Right? So this was capturing the problem for order graphs, right? And you can see that it was also capturing the problem for cyclically ordered graphs, because all you have to do is replace this with cyclic order. Or more generally, this is capturing the setup for graphs with extra structure that I promised you, right? So if I said, well, let's suppose that I is the composition of two guys, and the first guy is a structure raising interpretation that says, well, graphs can be interpreted into graphs union some extra structure. This P prime is some extra structure, or whatever that is. And then on top of that theory, I forbid some subgraphs with extra structure, whatever that is. So then I have some maximum adding interpretation. I take the composition of both of them, and if I ask myself what was the value of this pi t of I, what I'm asking is, what is the maximum possible density of T cliques in F-free graphs with extra structure, right? Whatever extra structure is, right? You can tell me what the extra structure is, and you can tell me what the family is. Okay, so everyone on the same page at this point?
Yes, just a question. You use here the fact that clique is defined on the unordered graph, or defined on the graph without any additional structure,
yes.
right?
Yes, yes,
So
because
in general, you can put there something else rather than the density of T cliques, as long as it's something that doesn't a property of unordered graphs.
yes, yes, because once you apply this construction, now it's a graph, right? So then you can only compute densities of graphs in there, right? Because this construction I completely erases the information that is not pertaining to graphs. So then it doesn't make sense for you to say, let's compute the density of an ordered graph in a graph. That doesn't make much of a sense.
But you can compute the density of pentagons.
Yes, you could compute density of say, the Peterson graph if you want. You can ask this question as well. Okay. Now, you might also think that this is a much more general setting than graphs with extra structure, because this graphs with extra structure only appears if my open interpretation is of this form. But actually, the general setting, right, when I have a general open interpretation, it is actually essentially of this form. You might not be able to write it as A composed with S, but you can write it as the composition of three guys. S is, as before, is a structure raised interpretation, A is an axiomatic interpretation, and J is an isomorphism in some sense, which I'm not going to get into details exactly what is isomorphism here. But what's important is that any sort of open interpretation can be seen as just graphs with extra structure. And the way that you do this is essentially you look at this open interpretation here, and you form the theory that is, you just plug T inside the graph. So you form this disjoint union of theory of graphs with the codomain of this guy, and you put a certain axiom that makes everything work. It's not very important exactly the details of how you do this, but what's important is the general setting is actually essentially graphs of extrastructure anyways. Okay. The last thing that I want to point out is that has already been pointed out is that even though we talked about non-induced F-free graphs, this setup allows you to talk about induced F-free graphs or induced F-free whatever graphs with extrastructure, right? So you can even forbid induced copies, which means that even if you take the setup and you take the theorem that I'm going to talk about in a couple of slides, and you apply to usual graphs, no extrastructure at all, you're going to get an induced version of Erdos-Simonovitz. You get something slightly stronger than the Erdos-Simonovitz as well.
You're repeating
okay.
What do you mean by saying induced?
Induced graph, right? So an induced graph, F-free induced means that you cannot see the copy exactly. The non-edges also need to match. Right?
Oh, okay.
Right. So say an induced copy of P3 is not the same as a non-induced copy of P3, right? P3 being the path of 3 vertices. So this allows you to forbid induced graphs with extrastructure, not only non-induced. Okay. Okay, let's proceed. And here is the big theorem that says actually the same holds in terms of an abstract chromatic number.
You have a question on that.
Mm-hmm.
You have a question on the chat.
Oh, on the chat.
Well, yeah, you can read it to him, or it's.
Yeah, let me just.
Okay, Leo, you see it or you?
Oh, yes, I can see. Are you saying this will give the Chromo-Steger statement for induced graphs then? Well, I don't know what's the Chromo-Steger, but if it characterizes the edge density in terms of if it characterizes the maximum edge density in F-free induced F-free graphs, then yes, it will give exactly that. Yeah, I'm not familiarized with exactly this theorem.
Oh. So we will keep it for after the talk. Yeah.
Mm-hmm. Okay, so so here's the theorem for the general setting. So you have an open interpretation again from the theory of graphs to some theory T, and remember this was saying maximize T cliques in anything that comes from this open interpretation, right? And let the size go to infinity. Now the theorem says that the density that you see is exactly what you would see in the Erdos-Simonovitz and Alon-Schickelmann theorem. So this is corresponding to the density that you would see on the Turan graph with chi I minus 1, where chi I is this abstract chromatic number. And the formula is down here. So I'm going to parse this formula in a second, but let me also point out that now you have some sort of weird splitting of cases going on here. And this is just a technical detail because, as I said, in this general setup, it could be true that there are not arbitrarily large objects. And when there are not arbitrarily large objects, when you try to compute the maximum, you get an empty set, and then it becomes minus infinity with the soup of an empty set. And the chromatic number is going to be able to detect that somehow by saying the chromatic number of this thing is 1, and then the density is minus infinity because you don't have arbitrarily large things. So this is that small difference. Now, let's go to the formula. So this formula is a little bit of a mouthful. So let me give you an informal description of this first, which is chi I is L plus 1, where L is the largest possible number such that you can obtain all possible supergraphs of the Turan graphs with L parts on all possible sizes. So let's see how this formula is actually saying this. So it's saying maximize the L.
Can you say it again? Even what we are going to this example. So just read this chi of I is L plus 1 again.
Yeah, so you find the largest possible L such that you can obtain all supergraphs of all Turan graphs on L parts on all possible sizes, right? Because you have a Turan graph on L parts can have different sizes. You look at all possible sizes, you can obtain a supergraph of the Turan graph from L parts for each of the sizes through your open interpretation I. Right? You find this maximum L and you add 1. This add 1 is just a technical detail so that it matches the previous chromatic number when you apply it to the usual setting. So this plus 1 is just a static.
Sorry, can you
A
say again?
supergraph is it has more edges. You can add edges. So for instance, a clique is always a supergraph of any graph. You add it. Supergraph is just adding edges.
Can you say again what this through I means?
Oh, true. Remember that this I here, it says every time I give you a model of T, I can construct a graph from it, right? So that's what I mean when I say true I, right? So you look at, so let's look at this formula for a second, right? So you're going to maximize over L. For every size n, you're going to ask, does there exist a model of size n in my theory such that when I apply my construction I see a graph that contains the Turan graph of size n in L parts, non-induced. So this contained here is non-induced. So that's why I said supergraphs as well. Is that clear?
Can you give an example? Do you have a...
You take an ordered graph from your theory T, you erase the orders and see whether it contains a Turan graph with appropriate L.
Yes. That is kind of the idea. Okay, if you think this is too abstract, you're not alone. You have reasonable, you have good reasons to think that this is abstract, and the reason is coming in the next slide. So let me point a couple of things before I proceed. So first, I want to say that the case T equals 2 actually already appeared. It was a previous paper of ours. It appears as an example there because we were trying to give an example of how these open interpretations work. And let me also say that the most traumatic part of this theorem is understanding the definitions. Once you understand the definitions, the proof is not that hard. You can reduce this to the usual Erdos-Simonovitz theorem of graph theory. You can just manipulate this definition and you can get this theorem. It's not, the proof is not that deep. It's just understanding the definitions mostly.
Sorry,
now,
one question. Is it possible for you to state the definition of the usual chromatic number in this language of supergraph of Turan graphs?
Yes, but it takes a little bit of effort because here we are doing forbidden induced graphs. It's not entirely clear how the usual chromatic number comes from this. There is a proof, but it involves a little bit of work. I will talk about the induced case at the end, and maybe I'll talk a little bit how you get the usual chromatic number out of this thing. But it would be a little bit circular because the proof of this reduces to the original Erdos-Simonovitz theorem. So technically, you already need to know that that is true. So it's not really fair to say, oh, let's use this to prove the Erdos-Simonovitz. The proof of this uses it. Okay, but it does follow. The usual chromatic number does follow, but it's not entirely obvious that it follows from this definition. Okay, so I see that this formula is traumatizing people, and it's not for no reason, right? So because if you think about this formula, right, and say that I want to think of it algorithmically, right, and say that I want to decide whether the chromatic number is at least L plus 1. Well, by looking at the formula, what I have to do is I need to look at all possible sizes and check whether there is a guy that realizes the Turan graph, right, or a supergraph of the Turan graph. In particular, it's not even clear that an algorithm for this exists, because an algorithm would have to say, well, let's check all the ends, but there's infinitely many, right? The algorithm doesn't stop, right? So this formula for terms of algorithms is completely useless, right? The only way that you can prove that I is greater or equal than L plus 1 is not with an algorithm, it's with an actual proof, right? So it doesn't give you an algorithm. So if we want an algorithm out of this, we might as well try to give a different formula for this. So let's ask ourselves, right? So let's assume that the chromatic number is at least L plus 1 for some L. then you could ask yourself, well, I'm guaranteed that these models that contain Turing graphs exist. What do they look like? Right? That would be a very nice question to ask. Well, if you work a little bit with extremal graph theory, you will know that this sort of question is very, very hard to answer, especially if you're asking in general. If you're asking for an arbitrary problem, you don't stand much of a chance to answer this question. So instead, let's rephrase this question slightly, which will make it possible to be analyzed. Let's ask this instead. If I know that the chromatic number is at least L plus 1, what are some n that must exist, right? I'm not going to characterize all the guys that contain the Turing graphs, but I'm going to say, at least if I know that at least one contains, this guy must appear. Right? So I'm essentially talking about unavoidable small combinatorial objects. And this is very well studied in combinatorics, namely the classic Renzi's theorem says something about this, right? Because if you recall, Renzi's theorem says for every k and m, there exists an n large enough such that if a hypergraph of size at least n, if I have a hypergraph of size at least n, then it either has a complete hypergraph of size m or an empty hypergraph of size n, right? And what Renzi's theorem is talking about is that essentially unavoidable patterns, right? For every m, every sufficiently large hypergraph contains a uniform hypergraph of size n. And here uniform is a different notion of uniform. What I mean uniform is that either everything is an edge or everything is a non-edge. That's what I mean by uniform in this particular sentence. Now, in our setting, we're talking about Turing graphs, but we're also talking about Turing graphs coming from some arbitrary universal theory. So what we want to talk about is a generalization that both holds in this general setting and somehow holds in a partite setting as well, right? Because the Turing graph has this natural partition, and the Turing graph is not a complete graph. So you shouldn't expect to see a Renzi theorem that as it is, right? Even if you don't have extra structure, you don't want to talk about complete or empty graphs. You might want to talk about something that is partite complete, maybe, right? So what we want is a theorem that kind of looks like this. If I give you some universal theory D and I give you parameters L and M, there exists an n large enough such that every time I give you this model M, so a combinatorial object, and I partition it into L parts, and all of the parts are large, so they have size at least n, then I can find a subset. And if I restrict my attention to the subset, then I see a partite uniform model, whatever that is, and on the induced partition, and all the sizes are kind of large. They have size at least n. Right? So m is given in advance, and I find this n. This is kind of the theorem that I want to find in this general setting. Is everyone clear about what? Is it clear that what is the kind of appearance of the theorem?
You can even define it in the theory of graphs, what you are asking for, right? I mean,
yes, in fact, that's my next slide. I'm going to say, okay, so how let's look at the case of graphs and let's see what happens there. But before I proceed, does anyone have any questions at this point? Okay, so let's consider a very simple case, the case of graphs, right? So and very simple. Let's think that we have a two partition. I give you a large graph, and I partition the vertex set into two parts. Now, this partition is not necessarily proper, it's just an arbitrary partition, right? And let's say that I want to find a graph that has m vertices on each of the parts. Let's say that m is 3 for simplicity, right? What are the things that I cannot avoid all at the same time? Well, if you think about for some time, you're going to see that there's a total of 8 patterns that you cannot avoid all at the same time, right? So you're either going to see completely empty, no edges at all, or you're going to see a triangle in the first part and nothing in the second, or a triangle in the second, or a complete bipartite graph, or you're going to see 2 triangles, or you're going to see a triangle in the first and a bipartite graph between, or the same thing the other way around, or you're going to see complete everywhere. Right?
But the point is that on every part, it's either a clique or an independent set.
Exactly, on every part and between the parts as well. So what is actually going on is that the reasoning that you're doing is, oh yeah, I should say, this, I said n equals 3, but for n equals 5 is exactly the same picture. It just looks more polluted. But what the reasoning that you're doing here is there are 3 types of edges in a 2 partition, right? There are edges that are contained in the first part, edges that are contained in the second, and edges between them. Right? And what you're saying is that these unavoidable guys correspond to saying, well, you choose a set of types of edges, and your unavoidable graph is going to correspond to that. So for instance, this guy here is the guy that all the edges of this type are there, and all the edges of this type are there, but none of the edges of this type are there, right? So what is going on here is that unavoidable subgraphs corresponds to sets of types of edges. Right? And this holds in general. If I give you an L partition, then you have a total of L plus 1 choose 2 types of edges. You either are contained in one of the parts or you're between a pair of parts. And your unavoidable graphs are going to correspond to sets of those. Right? So that is how a 2-partite Ramsey theorem should look like. If you have a very large graph and you partition into 2 parts and both of the parts are kind of large, then you're going to see one of these 8 patterns, right? And more generally for L parts. Now, a slight different complication happens when you go to hypergraphs. So for instance, let's ask ourselves, what happens if I have a 3 hypergraph in a 2 partition?
Can you explain why is it unavoidable?
Oh, unavoidable just means in the sense of Ramsey theorem, right? So if I give you a very large graph and I partition its vertices into 2 parts, and both of the parts are large, then I need to see one of these 8 patterns, right? On say 5 vertices on each side. So I need to see
if you have never seen Ramsey's theorem, then this explanation will not help you. So this is should be separate.
Okay, so I'll go and check Ramsey's theorem.
Yeah. Okay.
Okay. Thank you.
So let's think about the case of hypergraphs. So say 3 hypergraphs, right? So let's do the same rationale here. If I have a 2 partition of a 3 hypergraph, this gives me 4 types of edges, right? So a 3 edge can be contained in the first part, or it can be contained in the second part, or it can have 2 points in the first part and 1 in the second, or 1 point in the first part and 2 in the second. And as before, the unavoidable hypergraphs are going to correspond to sets of these. So there will be 2 to the 4 guys, which I'm not going to draw here because otherwise it will take the whole slide. And in general, if I have a K hypergraph in an L partition, the types of edges are going to correspond to what are called weak L compositions of K. These are just L tuples that add up to K. So essentially what you need to say is a K edge, how many points does it have on each of the parts, right? This is completely determines the type of edge. And as before, unavoidable subhypergraphs will correspond to sets of those, so sets of types of edges. Okay, is everyone clear on this graph and hypergraph partite setting so far? Okay, so now remember that in our case for arbitrary universal theories, there is a slight caveat, right? Our predicate symbols, they're not required to be symmetric in general, right? So the case of graphs and hypergraphs are nice because they're symmetric, but in general, they're not symmetric. So we need to deal with the case that is not symmetric. So to deal with that case, let's draw inspiration from the simplest kind of theory that's not symmetric, which is that theory of tournaments, right? So if you don't know what a tournament is, you have a bunch of vertices. Well, you can think of it as orientations of the complete graph, right? So you have the complete graph, and each edge you choose an orientation in one of the directions, right? Now, this theorem of Erdos and Moser says the unavoidable pattern here is transitive tournaments. So transitive tournament is a guy that you can actually order the vertices. So there's a first guy that all the edges are oriented leaving it, and then there's a second guy such that all the edges are oriented leaving it, except for the one that goes to the first guy, and so on. It's the one that you can order. This is called the transitive tournament. And Erdos and Moser say that, well, if you have a tournament on n vertices, you cannot avoid a transitive tournament of essentially logarithmic size. You must have logarithmic size, transitive tournament. Now, as I said, the transitive tournament here, so this term is saying unavoidable tournaments here are transitive tournaments, right? Now, a transitive tournament is this guy that you can order. So let me flip a little bit the quantifiers here, and let me talk about this, a slight modification of this theorem, which is like this. Instead of having the order in my hands, right? Because if I have a transitive tournament, I can pick the order of the transitive tournament. Let me give the order to my enemy, right? So the adversary says, I'm going to give you a model that has at least n vertices, and I'm going to give you the order. And you have to find a tournament that either all the edges agree with the order or all the edges don't agree with the order, right? So I let the adversary pick the ordering, and I still can find a transitive tournament in this sense, right? So of course the bound here is slightly worse because my adversary has more power. It's not really logarithmic, it's something else, but you can still do this, right? This is going to be very inspirational for us in the general case. So bear this in mind. We have this order thing, and what I need to do is to find something that matches this order somehow. Now, let's think of one more case that is slightly more general than tournaments to try to think of what happens when you have the partite case. So let's think of directed graphs. So for directed graphs, I'm going to talk about orders, but I also want to talk about partitions at the same time. So I need this definition that is slightly weird, but it makes sense. So this is the definition of L-split order. So an L-split order is a partition and order at the same time. So it's a pair. F is encoding a partition, so it's a function to L, so it encodes an L partition. And this thing is an order, but it's a partial order that only compares guys in the same part. Right? So it's a partition in which there's an ordering of each of the parts. So each of the parts gets ordered somehow. Now, with this definition, you can ask yourself the Renzi version of this, right? If I give you a very large directed graph, and I partition its vertices into two large parts, and each of the parts I order the vertices somehow, what are the things that are unavoidable? Well, again, let's look at the types of edges. You have 6 types of edges now, right? So you have an edge that is contained in one of the parts, but then you need to say whether it agrees or it disagrees with the order, right? So you have the decreasing edge contained in the first part, and you have the increasing edge contained in the first part. These are 2 different types of edges. You have edges between the parts. Here, you don't need to care about orders because there's no order between vertices in different parts. And you have the other case as well, the edge in the other part, and you have 2 types of it. And as before, the unavoidable guys, let me rephrase that before we talk about unavoidable guys. So another way of seeing that these types of edges is these are L split orders of the set 1, 2, right? Because what you're saying is that, well, an edge is going to be a pair of vertices. And you're saying, well, where do each of these vertices land on my partition? And if they happen to land on the same place, I need to also tell you what's the ordering. So this essentially is encoded by an L-split order, but now of this set 1, 2. Right? And as before, the unavoidable directed graphs are going to correspond to sets of these types of edges, sets of L-split orders of 2. Okay. Now, with this definition, I can finally talk about the general case. I just need a technical assumption, which is that no predicate is true on a non-injective tuple. So these are what are called canonical theories. Is a completely technical assumption because every universal theory is actually isomorphic to some canonical theory. I'm not really going to dwell too much in this. I'm just going to give you an example. So for instance, a classic example of a non-canonical theory is graphs with loops, right? In graphs with loops, you're allowed to say EXX, where E is the adjacency relation. Well, but you wanted a canonical theory. So instead of doing that, you're going to encode the graphs with loops by saying, well, it's just a simple graph and you have an extra unary predicate that is true whenever you have a loop. So that's how you encode graphs with loops into a canonical theory. And this can be done in general. But I'm not going to dwell too much on this. And let's see what the general case should look like. So first we need to encode the types of tuples, right? And this is encoded by what's called the L-Renzi pattern, right? So you remember you have this language L that has these predicate symbols, and for each predicate symbol, I want to look at the types of tuples for that predicate symbol. So a Renzi pattern is going to map each predicate symbol into a set of types of tuples, and these types of tuples are L split orders of this bracket scale, right? Numbers 1 through Kp. Kp here, remember, is the arity of the predicate. So these L-Renzi patterns are encoding types of tuples for each of the predicate symbols. And as we saw before, these sets of types of tuples should correspond to my unavoidable models or my uniform models. So that's the next definition. If I give you some Renzi pattern, and I say I have a model and some split order of this vertex set, I'm going to say that this guy is Q uniform if the tuples that I see that satisfy the predicate are exactly the ones that have the type matching my Renzi pattern. So there is this big formula that says something. So don't bother too much about the formalism of it. Look at this topic here. It says, in my Q uniform model, P is going to be true for a certain tuple if and only if the type of the tuple is in the set QP, right? So this QP is a set of types of tuples and is going to be true if and only if the type is that, right? So this is how you encode this more general set.
So Leo, let me stop you. Maybe you can say just something very high level about the plan of this proof, because you have given lots of definitions. You've essentially, talked about various ways of finding unavoidable structures, which you are going to use, obviously, in this reduction. You eventually want to take an arbitrary theory and, say that you can prove the analog of Erdos-Simonovich theorem because it holds in the, in the undirected and directed graphs, right? So this, I guess, this definition is helping you. You set up the formalism, but it was, a bit complicated and fast. This is going to help you to do this reduction to the.
Oh no, actually, the reduction. I'm not really going to go into details of the reduction because the reduction is easy. What this is helping me to do is to give an alternative formula for the chromatic number, one that is actually.
Okay, I got it. Oh,
so the reduction actually doesn't require any of this.
Okay, good. I got it. Okay.
Yes.
Yeah.
So the problem is that even to give the alternative formula, I need these definitions because the alternative formula uses these notions and says you should look at these and this Renzi pattern and do this and this. And then the chromatic number is computed like this.
Okay, and the other request is we had asked you lots and lots of questions, but I hope you can wrap up in 5 or 10 minutes.
Okay. Right. Okay. Let's see. Okay. So I'll skip some of the part of the end. Okay. So this is the definition of Q uniform, and then with this definition, you can prove a Renzi theorem. So let me not go into too much details of this, but essentially what this is saying is that, well, if I give you a model M, and I give you some L split ordering, such that each of the parts is at least n, so this is what this definition is saying, each of the parts are at least n, then you can find some submodel over there that is Q uniform with respect to some Renzi pattern. So what this theorem is essentially saying is that every large partite model has a uniform partite submodel. So just take this sentence out of the slide. It's not really important to understand every small detail of this thing.
So a question, was this even known for graphs?
Some version of it was known. So there's this general theory of Renzi theory for systems, for set systems, and you can derive this theorem for usual graphs from that theorem. And I think you can even derive it for hypergraphs. Yeah, for hypergraphs, the partite version for hypergraphs you can derive for that theory. From that theory, you can also derive. Maybe I'm confusing myself. No, sorry, I confused myself. You can derive the non-partite version of this theorem for arbitrary universal theories from this Renzi theory of systems. But there's also a partite version of Renzi theorem that has already appeared in the literature. But putting these two together, at least when I was looking into the literature, I couldn't find it. But again, let me also point out that this theorem is not that deep. It's just you have to just take the usual hypergraph Renzi theorem and keep applying it several times and do small tricks, and you can prove this. Of course, if you want good bounds, that is not going to go like that. But But if you just want to show that an n exists, then you can just keep repeating Ramsey applications and do small tricks, and you can get this theorem. Okay, now what does this have to do with the abstract chromatic number? Well, there are two particular patterns that are important for us, right? So remember that in our setting, we have graphs with X structure, right? Which means that there is a particular predicate symbol that is binary that's encoding our edges somewhere in my theory, right? So there are two types of patterns that are going to be very important. The first are complete patterns. These are the patterns such that when I look at Q uniform guys, they are complete graphs, right? So these are non-partite patterns, so one Ramsey pattern, so they're non-partite. And the Q uniform guys, when the pattern is complete, are the uniform graphs. The graph part is complete. So, and the other type of pattern that's going to be important for us are the Turan patterns. These are the guys that when you look at the graph part, it looks like a complete partite graph. Right? So these are the two types of patterns that are going to be very important. It's the E-complete patterns and the E-Turan patterns. Okay, and the last definition that I need to give before I proceed to the alternative formula of the chromatic number is this. You can do this operation kind of in reverse, which is if I give you some model M, I can ask myself, what are all possible patterns such that this guy is uniform against? Right. So this is what is called the L uniformity set, is the set of all patterns such that there exists some split ordering of its vertices such that N looks Q uniform in that split ordering. Okay? And if I have a family, I'm just going to say that the uniformity set is the union of those. Now, this definition is important for two reasons specifically. First, if I give you some structure M, it's easy to compute this uniformity set. Well, easy, not efficiently, but you can compute it with an algorithm. Because all you have to do is, well, enumerate all possible split orderings, enumerate all possible patterns, and check whether it's actually uniform. Right? So this thing is computable, and it's very important for us. And the second important property is that if I give you a family F, these uniformity sets are essentially saying something about whether form F has very large Q uniform guys. Because this guy has very large Q uniform guys, if and only if this particular pattern here is not in the uniformity set of the family. This is why this definition is important. Finally, I think I can present the alternative formula for the chromatic number. So if you don't remember what was the chromatic number, here's a reminder. So for instance, if we're trying to maximize the number of edges on this graphs with extra structure thing, the theorem was saying, well, it's the same thing as Erdos to Simonovitz, but you have to use this weird chromatic number, which was this formula. Now here is the alternative formula for that. You start with some open interpretation, and then we saw, well, every open interpretation, you can see it as graphs with extra structure, right? So let T prime be this theory of graphs with extra structure that's being encoded. And we also saw that every theory can be written as form F for some family F. So let F be this family. Then the chromatic number is computed like this. You look at the one uniformity set and you check whether this family contains all possible complete patterns. If it does not contain all possible complete patterns, then the chromatic number is infinite. Otherwise, you find the smallest L such that your family contains all possible L Turan patterns. Okay, so that's how you compute. Now, let me give you an intuition of why you would expect this to be true. Even though the proof doesn't go this way, it's a good intuition, right? What happens if you don't have a complete pattern? Well, if you don't have a complete pattern, by the previous slide, there should be a very large Q uniform guy of this complete pattern that you don't have. But this very large Q uniform guy that you have in your theory, the graph part is a complete graph. Therefore, if you're trying to maximize edges, there is a guy that the graph part is complete. So the maximum possible edges should be 1. The density should be 1. So if you look at this formula, the chromatic number in that case should be infinity. Right? That's the only way this formula is going to give you 1. Right? So that's what happens in this case. In the other case, the usual chromatic number is saying something about, well, it's all about trying to find a Turing graph with many parts, right? And this chromatic number is saying, can you find Turing graphs with L parts in arbitrarily large sizes? Well, this is about talking about Turing patterns of size L, right? So if you don't have the Turing pattern of size L, then you have arbitrarily large Turing graphs on L parts. So that's why this should be true. The proof doesn't go like that, but that's the intuition of this formula. Now, you might think this formula is actually just as bad as the previous one because you have to introduce all these concepts of Ramsey theory to say this formula. Well, but there's an advantage of this formula. And the advantage is that if this theory T has finitely many axioms, then you can produce a family F that is actually finite. And you can do it with an algorithm as well. If I give you the axioms, there's an algorithm that reads the axioms and produces a finite family out of it. And we have seen that these guys here, they're completely computable for each of my members of my family, and my family is finite. So I can compute these guys, and I can compute this chromatic number as follows. I first check if this is true. If it is, then it's infinity. Otherwise, I find the least L such that this holds. Now, you might be asking yourself, well, what if none of these L's hold? Well, actually, one of these L's actually does hold. This is a minimum, it's not an infinite. You can prove that this particular case, this set is non-empty. So this is important, but I'm not going to get into details why it's a minimum. So this formula is actually what allows you to say that as long as your theory is finitely axiomatizable, there's an algorithm that computes this thing. Now, the algorithm can be pretty bad. In general, the algorithm will be pretty bad, but there's at least an algorithm. Okay, so let me maybe finish by giving an example of this, which is the induced Erdos monoids that I promised. So maybe that is the theorem that was mentioned, that's already in the literature. So if I'm trying to do an induced Erdos monoids, this is the setup, right? So I have the open interpretation from the theory of graphs to the theory of induced F3 graphs, right? And it acts identically on the edges. Now, my theorem said that all that I had to do was to look at this weird formula here, right? Okay, let's reason about this, right? So if I have my family F and I'm asking whether I contain or not the complete patterns, this is essentially asking whether or not my family contains a complete graph. Right? And over here, if I'm asking whether my family contains a L-Turing pattern, this is essentially asking whether my family contains a complete L-partite graph or not. This means that in this particular case, this chromatic number takes this form. If F does not contain a complete graph, then the chromatic number is infinity. If F contains a complete graph, then the chromatic number is given by the minimum L such that the family contains an L complete graph. And that gives you the induced version of the Erdos monoids. Now, if you wanted the usual Erdos monoids, you can actually use this formula to produce that. And you can say, well, start with a family that you're going to forbid non-induced. Well, to get the family that you're going to forbid induced, what you have to do is take this family and close it upwards, right? You add all the possible supergraphs. And you can see that this property, what you're actually computing here for this thing that you closed upwards corresponds to computing the chromatic numbers of the guys in the original family. You have to work out the details, but it does work. And in fact,
but it will give the usual chromatic number.
It will give you the usual chromatic number of the original family, not the one that you closed up.
Yeah.
Essentially because when you say that something is C-colorable, what it means is that when I close it upwards, I can never see a complete graph on L-1 parts. A supergraph can never be a complete graph on L-1 parts if you color with L colors.
Yeah.
If the chromatic number is L, not that if you color it with L colors, but if the minimum number of colors is L, then you can never see an L-1 complete graph. Okay. Let me also point out that if you're trying to do other non-induced cases, right? So if you're trying to say ordered graphs, but you forbid non-induced, there's a way of simplifying this formula again in that setting. And this is what allows you to recover the usual interval chromatic number and cyclic interval chromatic number that we have seen. So that's basically what I had to say for today. I have a couple of open problems. I don't know if you have time to cover them. Right?
Open problems you can ask, yeah, sure.
Yeah, I can briefly cover them. So one, I said that the Runzi numbers, the proof is just repeated number of repeated applications of the usual Runzi theorem. So the bounds that come out of this proof are terrible. So this is a very natural open problem. Give better bounds there. Another one is that the way that I define Runzi numbers here corresponds to essentially the diagonal case. So you can ask yourself, what about the off-diagonal case? And the third problem is a property that I did not get too much into details, but is that of principality. So here's what this property is. If you are in the non-induced setting, right? So you have graphs with extra structure, and you forbid some non-induced subgraphs with extra structure. Then you can ask yourself, well, if I compute the chromatic number of this family, is it true that is equal to the minimum of the chromatic numbers of each of the guys in my family? Right? This is called the principality property. Now, you can ask yourself, what are the theories that satisfy this principality property? Because, for instance, when we saw graphs, that was the usual Erdos Simonovitz, and it was true that the chromatic number of the family was the minimum of the chromatic numbers of each of the guys. The same thing held for ordered graphs or for cyclically ordered graphs. But in general, this does not hold. And it was already known for the case of edge-ordered graphs. They had already observed in the original paper that this property doesn't really hold. If you compute of a family, it might be completely unrelated to the guys in the family. And in fact, you can find even easier theories in which this already breaks. If you have a graph and you color its vertices with two colors, it already breaks this property. So the natural question is, what theories have this principality property? How can you characterize them? So that's all that I had to say for today. Thank you.
Okay, thank you very much, Leo. From everybody. Questions to Leo? So what other theorems in extremal graph theory or extremal set theory that have similar characteristics can you have? So here we have some forbidden structures, and they are characterized. The density is characterized by a chromatic number. Is there another type of results of this nature that you think can be generalized or?
Oh, so far, not really, because, well, we would have to look into the literature to see if there is some pattern that is emerging, and maybe you can say, oh, actually, this is part of a much more general phenomenon that is going on. This was the first one that I've seen.
Okay.
So also, you mentioned earlier in the talk that these ordered chromatic numbers have fast algorithms, whereas the most general chromatic number, I mean, we believe this is hard. Any clue as to, what property tells you how quickly something is computable?
Well, no. So for something to be computable, you need this theory T to be finitely axiomatizable. Now, of course, the result that I presented to you here only says that if it's finitely axiomatizable, then it's computable, right? So you could ask yourself, is there something that is not finitely axiomatized?
No, sorry, I meant I meant computable fast, as in polynomial time and
efficient computation. Well, that would be a much harder question, and it's a very natural question to ask. Now, in the case of the interval chromatic number and the cyclic interval chromatic number, there is a particular property that you look at when you have this abstract chromatic number in mind, or rather the non-induced version of it in mind. And the property is that sort of like when you look at a Q uniform model of this guy, it's very easy to determine the uniformity sets. Because, as I said, the computability came from the fact that these guys here were computable, right? So essentially what you need to say is that your theory is so nice that there's a very fast way of computing these, and reason about these. And that is sort of what is going on the interval chromatic numbers. But at this point, I don't have any theorem to say, oh, you need this. But at least at an intuitive level, it's what seems to be the case.
Yeah. And in
why that-
particular, your approach can generalize the result for the cyclically ordered case, I guess.
Yes.
To
So
some
again, yes, I should say that even if you take there's a non-induced version of this chromatic number, but even that formula, both the interval chromatic number and the cyclic interval chromatic number don't follow immediately from that formula. You need to do some argument on top of that, in the same way that you need to do an argument on top of this to say it captures the original chromatic number. Right? So that also means that in general, even if you're just doing non-induced, a priori the general formula is not the best formula you could get for your particular case.
Okay, more questions. Okay, thanks Leo again. See you soon.